Now that we got familiar with the philosophy of seismic design, let's look at how this philosophy is integrated with seismic design of Eurocode 8. The code that we followed officially is called BS, British Standard, EN, Eurocode 1998-11-2004. 2004 was the year that it was developed, and you can see now about 17 years has passed, and our research hasn't stopped in these 17 years, so we know much better about our structural behavior and how to design our buildings. But anyhow, the official code, if we want to follow the code for seismic design in Europe currently is Eurocode. Americans have their own code, China has its own code, Japan has its own code. So many countries have their own codes, which are kind of a modified version of the American code. We will go through these codes as well, and we will see how they are. But now let's very quickly, let's review what the seismic design based on Eurocode 8 is, following the same concepts and philosophies that we discussed. Dissipation energy, ductility, capacity design, and see how Eurocode integrate these in. If you remember, the initial step of Eurocode was to get a response spectrum, the same response spectrum that you apply an earthquake to different buildings with different periods, and you see how they behave, so you get the spectral response spectrum or spectral acceleration of them. So Eurocode has applied thousands of earthquakes and has designed response spectrums. Those response spectrums, if you remember, were categorized based on ground type, from A, which represents rock, to all the way to E, which is very soft, loose soil. All of these are categorized based on how much the shear wave velocity is in their layers. So in rock is very high, more than 800 meters per second, but as you get looser and looser sand or soil or clay, you get slower and slower speed, 180 meters per second of shear wave velocity. So different countries have studied their soil layers, and according to that they have categorized their ground types. According to that, Eurocode or other codes have suggested response spectrums. Remember, Eurocode has annex as well, which depending on the country that you're applying the Eurocode, whether you're in Italy or you're in UK or whether you're in Greece, the annex will help change that ground type, and accordingly you will have a different response spectrum. The response spectrum which comes out of those formulations is the elastic response spectrum. So we still haven't got the discount. This is the actual response spectrum of our ground. This comes from the ground according to the period of the structure that we have. Taller buildings, Burj Khalifa; shorter buildings and stiffer buildings, White House. And then this is the spectral acceleration. In this case is normalized based on the peak ground acceleration and the soil type. Just looking at the different soil types, you can notice, and I know that you remember, that Eurocode divides the response spectrum based on type 1, which are surface magnitudes lower than 5.5. This is for countries which have lower seismicity. And then type 2, which is for countries which have higher seismicity, at least in Europe, for example Greece, for example Italy, for example Switzerland. They usually use type 2. As you can see, the graphs are a little bit higher as well. For example, in this case it stops at 4, while for type 2 it stops at 5. So higher acceleration will result in higher force, and higher force will result in bigger sections and more cost. As you can see, both of them are divided based on their ground types. You can see the rock has lower accelerations, while the soft soils D and E have higher acceleration. As expected, the wave of earthquake propagates through soil, soft soil, and it amplifies, while in rock it kind of stays the same thing as we discussed it in the initial slides. These are the familiar formulations. Just remember that looking at the title, the clause of Eurocode, which these formulations are given, or the future formulations are given, is always indicated over there, so you can refer to them. Again, remember, this is the horizontal elastic response spectrum. We have not talked about plasticity or any discount, just simply putting the period of the structure. You're able to derive the response spectrum. Again, as you can see, it's kind of a smooth curve, and we discussed that this is the average of a lot of earthquakes applied to a lot of structures with different periods, from all the way from 0 period all the way to, for example, 4 seconds. And this is the moving average of it. The formulation depends on peak ground acceleration, the soil type, and then some indicators of TB, TC, and TD. Remember, TD is where the displacement response spectrum becomes constant. For acceleration, this is the point which the spectral acceleration is constant. So I strongly suggest that you have a quick look at the displacement response spectrum, and you'll notice that at a point the displacement response spectrum becomes constant, like this acceleration. That is the point of constant. In some codes, for example in American codes, there is a high chance that you won't have TD. In some codes like Eurocode, they have introduced TD as well. But in most codes, you will definitely have the acceleration or peak ground acceleration, TB and TC. Now let's look at the real case. This was an earthquake of 2018. It happened in Italy. The records are from the National Institute of Geophysics and Volcanology of Italy, INGV. This is the response spectrum, the elastic response spectrum of the code, Italian code, 475 years return period. These are the three components of the accelerogram recorded, so north-south, east-west, and up-down, probably. And as you can see, east-west, north-south, and vertical, up-down. And as you can see, this was the actual response spectrum if that specific earthquake was applied to the structures with different periods. Just compare this to the response spectrum that Italy suggests. Does it match? Definitely not. So we can't always 100% trust that response spectrum, but anyhow, it is a good indicator. And remember, this comes out of thousands of these earthquakes applied to it. So be cautious while using the response spectrum. Now, beside the response spectrum, you have to find the fundamental period of your structure in order to go back to the response spectrum and read what is the spectral acceleration in order to do the forces and the next steps. Eurocode suggests a formulation, T1 equals C of T times the height of the building to the power of 3/4. This is for buildings up to 40 meters. For moment resisting frames, it suggests CT of this value. For moment resisting frames of concrete and steel, different ones, and other structures like if it's timber or if it has infills or anything, there are other values. For sure, again, having a single formula indicating all of the structural periods is not sufficient. So just a comparison over here is, if you look at these first bunch, these are like the 2-story buildings. This bunch are the 4-story buildings, and this bunch is the 6 and 8-story buildings. So different height of buildings. As you can see, this is the fundamental period. All of these are calculated based on modal analysis. So the actual T1 of the structure has been calculated. For example, just concentrating on the 2-story buildings, you can see the fluctuation goes from this much all the way to this much. So if I was using this formulation, they all have the same height. so H would have been 3 meter. They all were, for example, the same material, so CT will be the same. So all of these guys would have had the same, give or take, T1, while just concentrating on their values, one of them is moment resisting frame, one of them is a simple gravity frame, so no moment resistance in the connections, and some of the other ones have infills in them. And you can see the presence of infill have significantly stiffened the building, and it has reduced the period of the structure. The same thing happens with the other ones as well. Now this fluctuation or difference of let's say fundamental period increases with the height as well. You can see a great difference between these two cases, the moment resisting frame of a 6-story and a simple gravity frame, as well as when the infills are added. I don't think any of these values will cover this much difference. So you have to be cautious again. This is just an indicative formulation, again based on many years of study, but when you have the opportunity to figure out what is the actual fundamental period of your structure, conducting a modal analysis of your building, which you already know how to do it and you will practice it and practice it more and more, it's better to use that instead of this formulation that the Eurocode suggests. Now, so far we discussed about the elastic response spectrum. When it comes to inelastic response spectrum or the design response spectrum, the code allows us and gives us a discount. As I mentioned, when you use the elastic response spectrum, your spectral acceleration, depending on the period of your structure, will be higher. Then the code will give us a discount. Using a behavior factor, we reduce that acceleration to a lower acceleration, depending on whether the building is a stiff building or the building is a flexible building with different values, and you will design your building for a lower acceleration. Again, lower acceleration means lower force means lower section dimensions, lower section dimensions means more space, less material use, less time of construction, more money saved, happier client. So consider that the behavior factor as a discount behavior discount point that the code allows us to do. And the behavior factor literally simply takes into account the dissipative capacity and ductility of the structural systems, exactly as we discussed. The possibility of dissipating energy, as well as the material ductility and the material's nonlinear behavior. All of these combine and we get a behavior factor Q. And because it really depends on the structural system, it varies with structural typologies. For different structural types, reinforced concrete, steel, timber, different structural systems, moment resisting frame, brace frames, or simple gravity frames, the behavior factor differs. Because that differs, there are 3 different ductility classes which Eurocode suggests. The lowest ductility class is when you design your building based on the normal design codes of Eurocode. For example, you use Eurocode 2 for reinforced concrete. There's no lateral load because you don't have any seismic activity to consider, so you design your building for the lowest possible ductility. When we say lowest possible ductility, means your material is very close to just linear behavior, or you design it for Eurocode 3, which is for steel structures. When it moved to medium or high ductility, this is the place where the lateral forces, the seismic forces, come into play. For ductility class medium or DCM, moderate levels of ductility is permitted. is the most common type, at least in Europe. For ductility class high is for locations with high seismicity, more heavy detailing requirements are needed, and it allows for higher behavior capacity design factors. So we'll see a little bit on how these two are different, but just remember, we don't literally work with DCL. This is for the elastic design. This is for the gravity design. This is how the normal building without any seismicity is designed. When we move on to Eurocode 8, we have the medium class and the high class. So talking about ductility and behavior factor, Eurocode suggests this formulation. Using this formulation, you can get that discount code. So let's see how the discount code is calculated, and then we'll see how this discount code is applied to response spectrum to give us a lower acceleration and a lower force. So simply it says this is the formulation. KW has a value depending on whether the structure has walls or no walls, and then the most important bit is K0, which really is a relationship between how the initial plastic hinge in a structure is formed and how the plastic hinge mechanism of the structure should be. You don't need to know these so much. The guys who propose Eurocode have used these simple formulations, which is a relationship between alpha U and alpha 1 for different ductilities: medium ductility, high ductility. We discussed that the Q factor depends on structural typology. So you can see the structural types are divided: frame systems, meaning, for example, moment resisting systems; dual systems, which are like combination of different system, or coupled wall system, uncoupled wall system, torsionally flexible systems, inverted pendulum system. All of these, which we will discuss it a little bit more when we want to design our structure for steel based on Eurocode 8, has different values of Q factor or behavior factor. For example, you can see that Eurocode suggests 1.1 for this ratio for one-story building, 1.2 for multi-story one-bay frame, or 1.3 multi-story multi-bay frame. Majority of our buildings are in 3D. We don't have any buildings which are in 2 dimensions. So alpha U, alpha 1 is usually 1.3. If you're designing it based on ductility high, you multiply that 1.3 by 4.5 and you just bring it back to this formulation, and then you multiply it based on the QW from these clause. Whatever the result is, that would be your behavior factor. Again, remember, behavior factor was in direct relationship to ductility. Now, imagine that you have the behavior factor. We said that the behavior factor acts like a discount. Now, look at this response spectrum. Again, spectral acceleration, period of the structure. This is the horizontal elastic response spectrum. No discount applied to it. Now I apply my discount. For example, once my structure was something and I got a lower discount Q1, and once my structure was a perfect structure, steel structure, very flexible, very ductile, I got higher discount Q2. Simply the same formulations that we use to derive the horizontal elastic response, a Q is added to them, as you can see. So these Qs will bring the horizontal elastic response down. And now imagine your structure has this period. With this much discount, you have to design it for a very low spectral acceleration. With this much discount, you will have it at a lower acceleration than the original one. So this discount will result in lower spectral acceleration. Thus, lower spectral acceleration will result in lower forces. When we talk about forces, again, as you can see, this was the formulation, which you can see directly relates to mass, a factor, and that acceleration. So that force will be the seismic base shear force, which later on we will divide it onto different floors. As we mentioned, this exactly looks like the Newton's formula: force equals acceleration times mass. Now it's a little bit more complex. They have brought in a correction factor, but it's just a factor and depends on some simple measures. But mass will be the mass of your structure, and this is the design spectrum. Yes, this is not a displacement spectrum. Don't be confused with this. This is the design spectrum, means that the spectral acceleration that you got from the elastic divided by Q. After the discount, instead of the elastic response spectrum, you're using the design spectrum, which is SDT1. And T1 was from that formulation or the modal analysis that you do actually on your structure. So you know the period of your structure, you have the response spectrum, the elastic one, you apply the behavior factor, you get the design response spectrum, and you read your period and you get that acceleration. Knowing that acceleration, knowing the correction factor, knowing the mass, you get the base shear. Now we have to divide the base shear along different floors. A simple formulation is given by Eurocode, which really depends on the height of each floor as well as the mass of that floor, with the ratio of the entire height and the entire mass. See, summation of each floor's height times each floor's mass. Now, the question is, why do you think the top floors get higher seismic force while the lower floors get lower seismic force? This Fi is these blue ones, which is coming from the total base shear that we just calculated. This Fb is this. And then we just divided into different floors. So floor 1, floor 2, floor 3. Why do you think the force at the bottom are smaller than the higher floors? So think about this question and I'm sure you'll get to the answer, which is the concept that we always followed in the ultimate limit state design that Eurocode follows. So the resistance always higher from the applied forces, then your structure would be safe. There are some criteria for where this inelastic deformations are allowed, so where that weakest link should be, and they're very important, so let's read through them. There are 4 rules. The importance of element for the stability of other elements and the integrity of the whole. Yes, so we select the elements based on this concept that if that one fails, it doesn't affect the other ones. So the columns are the most critical ones, so they're the most important ones. Greater importance of vertical elements, columns, compared to the horizontal ones, beams. Yeah, as we knew it. Importance increases from the top of the building to its foundation. So the importance increases. So that means that the bottom of the building is the most important component. The accessibility of the element, how I can access it, and the difficulty to inspect and repair any damage. Again, a column which is hidden inside walls is much harder than a beam which we might find it and we can repair it, or a slab which we can easily repair it. So all of these will help us select the elements that I want the plastic hinges or ductility to happen, while other elements stay safe. Look at this case and this case. So this is a successful case that plastic hinges are happening mainly in the beams. This is an unsuccessful case that plastic hinges happened in the columns are failing, while other elements on top of it are strong and they're staying. This is what we saw in the Mexico earthquake. The bottom bits failed, the parking failed, because usually you have openings over here as well, and you have walls on the top. Very stiff structure on a very weak structure, the bottom bit fails, all of the structure fails. But this one is allowing the building to start dancing and dissipating energy, and if one of the beams fails, it doesn't affect the rest of it. Then there are some implementation of the seismic design philosophy, like having integrity in the plane, integrity in the height, which you can all study it, and the text is over here, so we won't go through them detail by detail, but like all of them are trying to avoid weak columns, strong beam. So they are all trying to apply the capacity design. Another important bit that Eurocode considers is the geomatic nonlinearity, the P delta effect that we discussed. A formulation is given, which is the interstory drift sensitivity coefficient. You calculate that, and depending on how much that value is, you will take different actions. Just remember, a structure, this is a graph of force versus displacement. So a force is applied to a frame, and we'll get the displacement. Excluding P delta, your building looks very strong. You see, high, let's say, capacity. When we consider P delta, suddenly you see the building is much, much weaker. Now imagine that if you ignore it and you think your building is in this blue line, then disaster will happen, because earthquake won't understand that you did a mistake. Earthquake will strike. Your building is weaker, you fail. Now it's important that this value is 10%, between 10 or 20%, 20 to 30%, or higher than 30%. If the P delta sensitivity coefficient or the interstory drift sensitivity coefficient is more than 30%, you have to redesign. It's too much. If it's between 20% and 30%, you have to do a proper second order analysis, usually using a software. If it's less than 10%, you can ignore it. It's not that much. Your interstory is not causing so much geometric nonlinearity. But if it's between 10 and 20%, it gives you a discount factor that you can apply to it and carry on the analysis. So it kind of increases the displacements and the stresses that you have, so your sections will be a little bit stronger. If you don't remember what interstory drift is, or if you don't remember what interstory drift ratio is, or as we call it, IST, in this course we're going to use these concepts a lot, so please make sure that you remember this. Interstory drift in this structure, height 1, height 2, floor 1, floor 2, is simply the displacement of floor 2 minus displacement of floor 1. You see, this was the initial structure. Load is applied. The structure is now bended toward right. I have a displacement here at floor 1. I have a displacement here at floor 2. Displacement of floor 2 minus displacement of floor 1 is my interstory drift. Now, if I divide this over the height of the floor, I'll get the interstory drift ratio, or IST as we call it. And it's usually presented in terms of percentage, while interstory drift is presented in terms of lengths, like millimeters, meters, centimeter. And again, Eurocode has an allowable interstory drift value as well, which you have to check it. Two important detailings that Eurocode suggests. One is for your beams and the other one is for columns. All of these detailings are making sure that the capacity design follows. So it makes sure that your beam is weaker than your columns are strong, and your beam has enough ductility to resist. Remember this, when you design a new beam according to Eurocode, you will have a different capacity in that beam. So you have to analyze the columns with new moments and shear. So you do not follow the same traditional way that you analyze your building and you use the same moment and shear diagrams for beam and for the column. The columns will have a new moment and shear based on the new beam that you have designed, which acts as the weakest link in your capacity design. Anyhow, the detailing is mainly related to the spacing of the hoops or the shear stirrups or the transverse reinforcements, whatever you call them. So we're talking about these guys which go around the longitudinal reinforcement. Yeah. So if you look at the beam, this long line is these lines going inside. These are the longitudinal reinforcement, steel reinforcements. The ones which occupy around them, they're called hoops or stirrups or shear reinforcement or transverse reinforcement. Different codes, different design concepts call them differently. The space of these are very important. As you can see, as they get closer to the column, the space reduces. and for different high class ductility or medium class ductility, there are different spacings. For sure, the high class has lower spacings, as you can see, as well as it defines a critical length where this spacing should happen. So you have different spacings in the middle, and you will have much more dense spacing of these hoops when you get closer to the connection of the beam to the column. All of these are to make sure that plastic hinges are shifted away from the column and it happens inside the beam. The same concept happens in the column as well. So if something goes wrong and the column is going to fail, we shift them away from the connections by having the critical length region, again for medium ductility and high ductility. The spacing of these hoops are very important. This is a 3D imagination of the reinforced concrete column. As you can see, the hoops are around it. This has lots of longitudinal reinforcement, so the hoops are a little bit more sophisticated, let's say 3 of them. And then if you remember, that degree of that reinforcement closure should be 135 degrees, not 90 degrees, which we used to do it in non-seismic areas. Also, the ratio of the reinforcement and the concrete is very important as well. It shouldn't be very less. There should be minimum of 3 bars in every side of the reinforced concrete column section, which the normal elastic design doesn't need that. The hoops will confine the central concrete. They will hug it from the sides, and it won't allow the longitudinal reinforcement as well as the concrete in the middle to get away. This is a very good method for making sure that the ductility of that section is met and the core, the concrete core, is safe. Remember, the concrete on the sides are called the cover. The concrete which is inside these hoops or stirrups or the shear reinforcement or the transverse reinforcement is the core concrete or the confined concrete. The concrete which is around it is the cover or the unconfined concrete, is not hugged. You see, any concrete in the middle of this hoop will be confined. Someone is hugging it. Any concrete outside of it is exposed. And if an earthquake happens, the cracks usually happen in the covers while the core is getting safe. Now, confined and unconfined, as you can see, stress-strain relationship. Confined gives a massive ductility as well as a massive strength. If a concrete or a concrete column or beam is not properly confined, you can see the ductility is very low and the strength is very low as well. So again, Eurocode has some formulations to make sure that you reach that confinement and your concrete becomes something similar to this. The last formulation that you have to check based on Eurocode is the confinement factor. So the confinement effectiveness coefficient. If this alpha is satisfied, your confinement is good. If it's not satisfied, this long formulation, which you have to always, this is the end point of your calculations. If this formulation is not satisfied, this will happen. Earthquake strikes, the spacing and the confinement resistance of these hoops weren't sufficient. As you can see, bend, buckling of all the steel reinforcement, and the complete failure of the bridge pillars, which is a disaster for whoever has designed it. You can literally see the core concretes getting out of it as well. These holes shouldn't existed, so they're all broken and they're taken outside. You can see it landing here.